that optimize the use of computational resources, both classical and quantum architectures. She analyzes, implements, and evaluates various algorithm approaches to address complex problems, refining each solution according to the specific requirements of the system or application. Her primary interest lies in developing quantum algorithms that effectively leverage the capabilities of quantum computing. I give the floor to Sandra Rosales.
Good afternoon, and thank you for the space. Well, let's go. I am Sandra Rosales, and I'm going to talk about the adiabatic quantum computation to tackle the tree satisfiability problem. Okay, so for a start, let's go to introduce a little bit about the quantum adiabatic computing, and this concept is based in a theorem, the adiabatic theorem, that explains that if you have a quantum system that it's governed by the equation Schrödinger, you can take the Hamiltonian that represents the energy of the system, and you can slowly vary this Hamiltonian, and you can obtain the ground state of the quantum system. So the way to obtain this ground state, okay, this is important because we needed to obtain the ground state of the quantum system, because in that ground state, you can obtain the moment and the energy. There are uncertainty called the uncertainty for Heisenberg that explain if you have the moment, then can obtain the energy of the system. But if you slow variable the time, you can obtain date. And Fari in 2014 developed an adiabatic quantum algorithm with this framework and established that you needed a Hamiltonian initial and Hamiltonian final, and you can obtain this Hamiltonian of this quantum system. Okay, and this Hamiltonian initial by convention in quantum computing is using the Pauli X. It's mean the X gate in quantum computing, and for the final Hamiltonian, you need the function original. Okay, okay. In this sense, we can see this is a function, okay, and Fari saw that you need optimize. So how we can optimize? Well, in this sense, create the quantum approximate optimization algorithm, because we need obtain this Hamiltonian, and this represents the slow energy of the systems. So we needed a minimize for one function of the energy. The quantum approximate optimization algorithm have an objective function. In particular, this framework is applied for combinatorial problem in general. And each value here is a clausule. In particular, for this problem is a satisfiability problem. And we have clausules, variables. That's variables can be, there is binary. And this binary, it can be represented by a qubit, okay? So the combinatorial optimization I specify by n qubits and m clauses. And this clausule is satisfied if 1 and 0 in other case, okay? Okay, how we can programming this in quantum computing, because this is very abstract. Well, we can transform this objective function with a matrix, okay? In this matrix, in the diagonal of this matrix, we can the value of our optimization function. So we have one parameter, but we need also one parameter called gamma, and we have another that is beta, and this beta is the convention of the Pauli X. So it's a matrix that we know, okay? And and this is a concatenation of these parameters, okay? And in this problem in particular, yes, we initialize the quantum circuit in a superposition, in particular in positive superposition. This we can do with the Hamiltonian and the qubit zero. Okay, so what is the satisfiability problem? In particular, the satisfiability problem is a problem classified in classic computation like NP, or just NP hard. No? So for that reason, there are many efforts to carry up or take this problem to the quantum computing, because it's a good candidate to show the good things for the quantum computing. Okay, so the manner to represent this problem is very important, because you have the clausus 1, clausus 2, and M clausus. And this is a very small example about how you can see these clausus. And the objective is know when we obtain the true values, okay? So this, every value in particular, we can see 0 or 1. But in particular, for this problem, we apply plus and minus 1. And this is important because when we apply this problem, generally we confuse when apply 0 or 1. This is 0 represent when it's plus 1, and 1 will represent the minus 1. In particular, every combination, we have 2 power n states possible for n variables, for x variable. Okay, so the representation very useful here for the satisfiability problem is with a matrix representation that also can be seen like the adjacent matrix of a graph. Okay, in particular with the Ising model, but more adelante. See you. Okay, so for example here, this representation, we can see that 0 is when in the clausus C don't have this variable, okay? And the clausus 1, we have the variable x, and this variable, that is the variable x sub 4, we have a minus because it's negate in this. So this is representation. It's very similar, like the representation of the energy. Okay. So with this in mind, we can see again this objective function that is the clausule, and this is the variables. Okay. So how is the relation with the ground state of the Ising model? Well, result that this Ising model is very useful to take the satisfiability problem, okay? And we can actually apply this formulation, and this formulation, I don't know, see, yes. Okay, this formulation is very useful to apply the operator that showed before, okay? And we can see this matrix, a graph, and if we can obtain the matrix adjacent, we can obtain a matrix similar like this, okay? So, okay, let's go. So we first need obtain this parameter, gamma and beta. And this is a concatenation of this operator. And this is the superposition in the initial, that is this point, the superposition positive. And the clauses here, it's the zeta. So let's go here, here. Okay, we can see that if we apply this, we can obtain this formulation, and we can use these parameters when collapse the system. And this using the trotteration approximation, because there are a different model, the quantum gate and the adiabatic model, and the difference is because the formulation for the adiabatic is using the Hamiltonian. But when physically you want to obtain the evolution of the quantum gate, you need a Hamiltonian also. So there are a difference important when we want to apply this model. For that reason, we use this approximation. So there are different hardware, quantum hardware to apply this model, and one of them is the D-Wave, and another is the Google Circ. A characteristic of Google Circ, a good characteristic, is free right now because IBM is have a cost right now. But this is very useful, and also have different quantum circuits online, and you can see the different configuration of the circuits, the quantum circuits. So in particular, we can see that this is a grid. This is not the new. The new, I think, is called Milo. And well, you only need install libraries, and a Word preferred with Linux, the preference. Okay, so how we can apply this circuit to obtain the results. Okay, this is important. This is speed time. This is the cyclic time. That means you should be alternate to different times, and this parameter you should be select. And also, we begin in these parameters with a seed. So also you need choose that parameters at the beginning. Okay, so iterate to obtain the best result. So this is the circuit already applied in quantum circuit. And we can see this is one iteration, this is another iteration, and also we can apply the difference. At the final, we have the X gate, and at the final, we can see some results. This is the old function of energy. We can see that this function of energy, or in particular the satisfiability problem, have many maximals and many minimals. The more yellow is the maximal energy of the system, and the more blue is the minimal energy of the system. So there are many points that you can see. For that reason, it's a good it's a good option. Choose the approximate optimization for this kind of problem. Okay, so when we run the quantum circuit, we obtain the different option. Here we only show the 50 most common outputs, and we can see that the string index, the bit string 0, that is the minus energy of the system, is obtained. So okay, so let's go to the conclusion. So tackle the satisfiability problem is useful for solving problems with a single approach. For example, travel-saving problems. This framework is an approximation. That means this is very important because it's not a solution optimal or maximal. It's an approximation, and can be very useful because we can address to good way, to good results. Okay. And also, this approach leverage the characteristic of the quantum device, because we can work with the adjacent matrix at the difference option. So it's very useful if you can understand some certain concepts. Okay, yes, there are a relation with the quantum adiabatic algorithm, but certain papers say that it's different. So we needed, it is important to mention that the quantum computing is still in developing, and there are many things that we believe, and I am sure that probably in the future near will be changed. But right now, this is what it is. And we can use this model in the similar way that the adiabatic quantum computing. So the challenge for this tackle is how we chose this. Well, in general, I think when you work with machine learning and the difference, you have parameters, and they say generally that you should be select something, and I know that it is experimentally, generally. So this is very expensive. Some papers explain that use the classic computing to obtain these parameters. So it's important to mention that. And also another thing important is how we can transform our problem, the quantum approximate optimization algorithm, how we can apply directly. In particular, the satisfiability problem, because it's a combinatorial problem that you can use the matrix adjacents, you can modelize like energy, but it's not the same for the another problems. So we need looking for a good proposal to apply this approach. And the future, well, expand these projects that are similar that the tree satisfiability problem, and well, more optimization problems like a path planning or something like that. Okay, so thank you for listening. Question.